morning, everyone. Is my mic okay? All right. Thank you for joining today. My name is Moez, and today we'll talk about an open source library called PyCaret in Python that I created 3 years ago, 2.5 years ago. So there is a code demo in this talk, this presentation, as well as all the notebooks that we'll create. I'll upload them on this GitHub link for you. All right, so a little bit about myself. My background is in finance and economics, and I've worked for almost 7 years, first half of my career in hospitals around the world. I've practiced economics, and then 2016 I migrated to Canada, where I decided to change my career from finance/economics to data science, looking at all the automation and everything. Currently, I work for a software company called Intuit in US, and we build machine learning software for forecasting at a scale. So companies like Walmart, Target, where use cases are really, really big in terms of data, millions, tens of millions of time series every day. Apart from my day job, roughly 20-25% of my time goes to PyCaret, which is an open source library. We have 90 contributors around the world, and a team of 10 core members who manage the day-to-day work of PyCaret. In addition to that, I also teach AI in clinical medicine courses in 3 universities in Canada. And I do teach AI course in MBA program at Cornell University in New York. All right, so our goal today is, we have a very small presentation deck where we'll talk about what is PyCaret, but a lot of time we'll spend on live code demo. And just so I get a sense, how many people here are data scientists or machine learning engineers? All right, very cool. So there is a live demo, and things can go wrong in live demo. I've taken the risk. Please be nice with me if something goes wrong. All right, so this is the AI and data landscape coming from Linux Foundation page. And you can see the way they organize this ecosystem is they divide into 3 categories: platform, framework, libraries. There's a technical difference between framework and library. In simple words, think libraries as functions that you would import and do your work, as opposed to frameworks, which are more lower level that you can use to build structures. You can see PyCaret appears in the library section here next to scikit-learn, and we'll see in a minute what is the problem PyCaret is solving. All right. So PyCaret is an open source machine learning library for building machine learning pipelines, data pipelines in Python, similar to what you can build using scikit-learn, except the difference is in PyCaret, you really have to write way less line of code. So something that you would achieve in 50, 60, 70 lines of code is liability. You would write a few lines, 3-4 lines in PyCaret to achieve that. In more technical terms, it's a declarative framework to build your machine learning routines in Python. Okay. The 2 keywords here is it is low code. That's the big differentiator compared to the libraries. It's very easy to use and adopt. There's almost no learning curve. And the second keyword here is citizen data scientist. When we were working on the project, our goal and the primary target audience was citizen data scientist. And over the last 2 years, what I've seen actually, even though it was targeted for citizen data scientists, we have seen a lot of use cases of PyCaret in consulting work where you need to build rapid prototypes for your client. We have seen a lot of use cases of PyCaret in sub $10 million companies, so small companies that do not have a full-fledged data science teams, companies that have a lot of data, a lot of software skills, but now they want to transition into monetizing that data. Okay. In last 2 years, we have around more than 300 citations, research citations on PyCaret, and we have seen use cases of PyCaret in many different industries, from life sciences to sports to physics. How many people here have already heard the term citizen data scientist before? All right, so this is a term invented by Gartner a few years ago. And the definition of this term is a person who is leveraging predictive or prescriptive models, but his or her primary job function is not statistics or analytics. That's the dictionary definition of citizen data scientist. And this picture is really good demonstration of it. You can see citizen data scientist is halfway between a business user and a data scientist. And the original pitch, when the term was invented 4 or 5 years ago, 6 years ago, was we would have shortage of data scientists in future. It's very expensive to hire, retain. Hence, citizen data scientists would have less technical skills, so they are less in technical persona, but they make up through their domain knowledge. Over the years, I have come to realization that it is not just a way to deal with supply shortage, but also now I see citizen data scientist as a prominent role in a team. If I have to make a team ground up, I would explicitly and intentionally hire citizen data scientist. Rather, I would hire business analyst and convert them into citizen data scientist. Okay. All right. So in machine learning, there are usually 2 phases, a training phase and a prediction or an inference phase. Training phase is where I always see data science as a twofold problem. There is a problem space and there is a solution space. Solution space deals with things like how to deploy this model, how to deploy it at scale, how to deploy it at edge, monitoring the model, observability, things like that. And problem space is where data scientists, citizen data scientists, would do a lot of experimentation and iteration over many different parameters, be it parameter of data or parameter of models. And they would go through this loop of training phase where they would try different things, and at the end of that process, they would come up with something which is known as model or a pipeline, to be technically more correct. And that pipeline is then used in a production environment on cloud or on-prem to score unseen data. So imagine you're building a model that can learn from X-ray images whether there are certain lung condition exist or not. In training phase, you will source the data, you will try different models, and you would come up with the best model that you want to put in production. And then once it is in production tomorrow, when you have new lung X-ray images coming, which are not, you do not have the diagnosis for them, right? You would pass those images through your machine learning model or pipeline to obtain the predictions, right? That's the reason you have built a machine learning model in the first place, so that you can score on unseen data that would come in future, right? But if we zoom into a training process, this is what a life cycle looks like. You start with a business problem, and for a good and valuable machine learning project, the early sign is people will spend a lot of time talking about business problem. This is the most important phase. You would hear people often talking data processing is the most important thing for machine learning, or it takes 90% of the time. I think it's 2 steps before nailing down the problem, quantifying it, finding a sponsor to sponsor your project, right? And then convincing people around the value, and then able to actually deliver that value. All these are very critical steps. Data sourcing and ETL is a process where you source the data from different databases, different data sources, in order to get to a point where you have some data to start working on. You get into exploratory data analysis, where you do a bunch of descriptive analytics. You check outliers, you do different kind of visualizations to draw stories. And then also exploratory data analysis help you to take certain steps in next step, which is data preparation, right? Imagine you find that a particular variable has a lot of missing values in your exploratory data analysis step. That would lead you to take some action in the next phase, right? And then model training and selection is the centerpiece of machine learning. This is where you throw your data at a bunch of algorithms, try a bunch of different parameters, and measure them. And at the end, come up with one out of 3,000 different models or 3 million different models, right? And this box around this, this diagram basically shows that you do this in iteration, right? So machine learning is a very iterative process, and one way to be really successful is to iterate a lot. And you iterate a lot, you'll fail a lot, right? So a tool that can speed up your process to fail again and again and try again and again would be very valuable. And if we zoom into just the box of model training and selection, this is more zoomed in version. You start with data, you do train, test, split, and then you do 10,000 different kinds of things. And at the end, when you have data ready, you try 10,000 different models and come up with one best pipeline. And pipeline is essentially a steps of transformations that is changing your data, and then model at the end that accepts the transform data. All right, so we'll see that in demo. PyCaret is end-to-end from data to model deployment in a low-code environment. You can do many different kind of pre-processing in PyCaret. You have many different kind of machine learning models in PyCaret. You can do hyperparameter tuning, model selection. It has integration with a very large ecosystem of open source libraries. When we started the project, we integrated a couple of open source libraries with PyCaret, so it is built on top of scikit-learn, XGBoost, CatBoost, all the favorite libraries that you use in your job. So think PyCaret as an abstraction layer over the top of all these libraries. So originally we started with few projects, integrated them, but today, because PyCaret got some early traction in its first year, today we are receiving a lot of integrations into PyCaret. So other open source project, they would send a pull request and create an integrator for PyCaret. So we have, I think, more than 60 open source projects now connecting to PyCaret. So it is now evolving as a very grand mega abstraction layer. All right. In terms of use cases, so PyCaret is pretty broad. You can do supervised and unsupervised machine learning. In supervised, you can solve classification problems. This is where you want to model discrete outcomes. So think about customer would default or not. Think about a patient has a particular condition or not, patient would stay alive or not. All those modeling choices where the outcome is discrete. Regression is where you want to predict a continuous value, sales, salary, or continuous value or quantity, as the statisticians will call it. Time series is where you want to model your time series. You want to forecast into the future. The difference between time series modeling and regression is in time series you are modeling based on the lagged values, as opposed to regression where you have this concept of you have features and then you have target. In time series, your features are the lagged value of time series itself. And then for unsupervised learning, we have clustering module, anomaly detection module, association rule mining, and NLP. We have a very small NLP use case. We only support topic modeling, which is an unsupervised NLP model. Yeah, so the first release, if I remember correctly, of PyCaret was April 2020. So it's a little bit over 2 years now. In last 2 years, we have gathered 6.5 million downloads, 6,500 stars, 90 contributors. So by the numbers, PyCaret is among top 1% open source Python libraries by downloads. These are all the integrations, and this is like 1 year old now. But we do have, obviously, scikit-learn is the main library that provides a lot of estimator. But then we do have integration with Rapids. Anybody have used Rapids before? So Rapids AI is an NVIDIA project. Scikit-learn models, you cannot train them on GPU. They are designed to work on CPU. NVIDIA has created a project called Rapids, CUML, which provides GPU implementation for all the algorithms. Not all the algorithms, some main algorithms of scikit-learn. So in PyCaret UK, there's a switch. If you want to use GPU or CPU, if you set the switch to true, we get a model from Rapids instead of scikit-learn. Okay. Ray is, anybody used Ray before? Ray is a distributed processing framework. So in PyCaret, when you are tuning hyperparameters and if you really have a large compute grid, you can distribute the workload by setting just one parameter. No configuration, no setup, nothing. And actually, we started with Ray, but very recently there's a project called Fugue. Anybody heard of Fugue? No. So it's coming out of Lyft, Lyft. And what Fugue is doing is what we are doing in machine learning space. Fugue is an abstraction layer over all the distributed processing frameworks. So we have a Spark today, we have Ray, we have Dask, and we have now integration with Fugue, which means that you can choose whichever engine you want to distribute your machine learning jobs. All right. How are we doing on time? Okay, I'm doing pretty good. Now is the time for demo. So I'm gonna code my demo in Jupyter Notebook, and Jupyter Notebook is, I don't want to call it IDE, but basically when you run Jupyter Notebook, there's a Python kernel running behind the scene, and data scientists use Jupyter Notebooks during experimentation phase because it's interactive. You type your code, you see the result, you make a decision, you type another code, right? And I'll show you if you have not seen before. This is what a notebook looks like, right? You have cells here and you can type your code and you will see the output. Okay. All right. So we are gonna first take a look at a regression use case where we are predicting. Let me just import the data. So is it legible? All right. So I am using the release candidate. We are release candidate 4, which is not a stable version. We are releasing PyCaret 3.0 in next 1 month. So I'm going to use a release candidate for this demo. All right. And I am going to take a look at this data set. Right. So what we have here, it's a very small data set, right? Each row here is a patient, and you have certain attributes on patient: the age, gender, how many children, smoking status, which region patient comes from, and then the charges, right? A use case of this might not be very relevant for North American, European countries where healthcare is public, but imagine countries like Africa, Asia, where healthcare is not public and people do not rely on insurance companies to pay their healthcare bill, right? They buy private insurance. Not rely on public insurance, but they buy private insurance, right? In a situation like that, imagine how important cash flow management is for insurance companies, right? So imagine you enter into hospital and insurance company knows that what would be your estimated charges over next 5 days, 7 days, and that would allow them to do very good planning of cash flow. Certain variables here, for example, gender, depending on the country, I don't think so you would be allowed to use that in machine learning model. Europe is extremely strict when it comes to use of variables like gender and age. I've heard that in Europe, banks cannot even collect the data regarding gender. I don't know how true is that. But in North America, banks do collect the data, but they cannot. There's regulation that forces them to not use that in decision making, right? But we'll ignore that for a minute. I have used this data intentionally because I want to show one of the functionality, which is basically measuring the bias of your model. Okay. So we have 1,300 patients, 7 columns. You can see some of these features are categorical, such as gender and region, right? Your machine learning models, you won't be able to pass this directly to your machine learning model. You would need to do some kind of pre-processing, right? And then it's a regression problem because we are modeling a continuous variable or a quantity. If you want, you can see the histogram. It's right skewed. All right, let's start with importing. All right, so when you're writing a production level code, you should not import through star. That would be very bad. But in Notebook, I think it works, right? But if you want, you can just import individual function. I'm gonna follow my own practice for importing star. The first thing you do in PyCaret is you initialize the setup. And setup function is very simple. It takes data, name of the target variable, and session ID. Think session ID as a random state, right? When you do your experiment, there's a lot of random elements from train test split to your hyperparameter tuning to ensembling, and some models also have a random state. And in machine learning, you really care about reproducibility, right? So random state, when you pass a session ID, we take this session ID and treat it as a random state and propagate it to all the functions, which means that if you run this code, right, you do your experiment, if you run this code, it would reproduce dot to dot all the same results, right? And reproducibility is really big thing. All right, I'm going to run this. Hopefully it will work. So when you call a setup function, what happens is behind the scene, there are setup function is used for pre-processing. So if you see the documentation of this, you would find there are a lot of things that you can pass into this, right? But there are 3 things that PyCaret does by default, which is needed. One is train test split, because we want to train the model using cross-validation on train set only. So there's a holdout set, which PyCaret do not use, right? If you want, before deploying model, you can check that model on a holdout set. But by default, PyCaret would only use a touch train set. The second thing PyCaret does, without which your model training would fail, is if there are missing values in your data, PyCaret will impute them. By default, we use simple imputer from scikit-learn, but we have many different imputation, like iterative imputation and many other different, some of the algorithms. So originally we started building our own algorithms, and I'm talking like 2 years ago, scikit-learn didn't have iterative imputer. Today, after 1.0, they have iterative imputer. But we built, in the beginning, we built a lot of original implementations that over time we just donated to other libraries so that PyCaret is focused on the abstraction only. Okay, so missing value imputation it would do. And the third thing it would do is looking at sex and region. These are categorical features. In order to model them, we normally, data scientists would do encoding. The most common type of encoding is called one-hot encoding, where you take these features and convert them into binary flags of 1 and 0, right? So these 3 things PyCaret would do by default. But if you want to change the imputation method, if you want to scale your data, if you want to transform your data, if you want to create features, feature scaling, feature interaction, remove multicollinearity, all these are just flags here, right? If you want to use PyCaret on GPU, it is as simple as you typing use GPU is equal to true. And now if you have GPU detected, PyCaret will abstract that entire process of setting up and would just point your jobs to GPU instead of CPU. There you see. I'm just going to use CPU for now. All right. So at this point, data is ready, right? We have a train set, we have a test set, missing values are gone if there were any, and one-hot encoding is done, right? The function, the first function that people usually use in PyCaret after setup is compare models. So what this function is doing is behind the scene, it is running a tenfold, by default, tenfold cross validation on all the estimators in the model library. And when I say all, it means scikit-learn plus XGBoost plus LightGBM plus CatBoost plus anything that is compatible with scikit-learn API, which is almost 99% of the ecosystem, right? And then what you see here is this table where each raw is a model. You might recognize these names: gradient boosting regressor, random forest regressor, etc., etc. And all these columns, except for the last one, which is training time, all these columns are metrics. And using these numbers, data scientists would make a choice if model A is better than model B. I'll keep it simple. We'll just talk about mean absolute error, which is basically prediction minus your true value with absolute, and you take an average of them, right? So looking at this table, this tells me gradient boosting regressor has a mean absolute error of 2701. The good thing about mean absolute error is the unit of this is same as your data. So in this case, you can interpret this like $2,700, right? You can, when you have something like this, you can always make a comment that gradient boosting regressor is doing better than all the other models. But if you ask me, how do I know if $2,700 is what I should accept? Can I improve further? Because there are 10,000 other things you can do to improve the score, right? I think the one very simple thing you can do is you can see in absence of a machine learning model, the best prediction is usually mean, right? So what you can do is you can see what's the mean of your data, right? It's 13,270, right? And then if you take 13,270 and minus it with each of the observation in your holdout set, right, and take an average of that, you would get a number. If that, and that, what that number would mean is it's a mean absolute error if you had used mean as your prediction, right? And if you compare that number with this number here, if this number is lower than that, which in this case it would be lower by much amount, that means that if you have a machine learning model which has a mean absolute error lower than your mean predictions, definitely you should go with the machine learning model, right? But all right, at this point, this variable best would have a model stored for us. So it's a gradient boosting regressor, right? If you check the type of it, it is a scikit-learn model. And the goal here for PyCaret really is not to reinvent the wheel, right? What we want to do is to replace the boilerplate code during experimentation, right? We don't want people adopting PyCaret to change their stack or technology, right? So they're using whatever they're using right now. PyCaret is just coming out to replace the boilerplate code. Okay. All right. So let's see what else can we do. So this is the residual plot for regression. Data scientists really like these plots, and really what we are looking at. I'm not going to go into technical details in this session, but after we build model, we check a lot of plots, and our goal is to look at them and go back and fix things in our model. For those of you who are data scientists, might notice something wrong in this graph here, right? We're not going to talk about that, but there are many other analysis functions in PyCaret, right? You can see your pipeline, you can see the residuals plot, you can see the error plot, you can see feature importance. So all the common things that you would write your code for, it's already prepackaged. Feature importance is another very important plot that data scientists look at. And what this tells us is, out of all these 6 variables that we had to predict the charges of patient, is smoker being the most important feature. This graph doesn't tell us if you smoke, your bill would be less or more. It doesn't tell you the direction, right? It just tells you the magnitude in relative terms. So that's like the downside of this, right? A lot of people consider feature importance as explainability method, and it's not truly a explainability method because it doesn't tell you the direction. So alternate for that is SHAP or a framework like SHAP or ELI5. Anybody here use SHAP before? All right, so we have integration with SHAP as well. And for that, I would just call interpret model. Let me just create a model. Create model is a function that trains a model and gives you, so in this case, we have created a LightGBM model, 10-fold cross-validation. That's why you see 10 rows, 0 to 10. The scores, the metrics are for each fold. Then you have mean and standard deviation. The scores that you see here, 2992, LightGBM, it would match with this, right? So when you call compare models, we don't show the results by fold, rather we just show you the mean result, because after all, that's what you care about. Let's just now call interpret model on LightGBM. All right, so this is, for those of you who have used SHAP, would know that in SHAP you can do global explanations as well as local explanations. This is a plot called bswamp. This is for global explanations. This tells you on x-axis you have each row is a feature, and then you have on y-axis you have a scale denoting that the higher the value of the feature is, it's red, the lower it is, the blue. And then here 0 is no effect, right? If you move right to 0, the model is going to increase the prediction number. If you're moving left, reduce, right? So this is just showing you impact. Very tricky to read, big learning curve to understand this. But if you already understand this and you are using SHAP outside of your scikit-learn code, this is one nice way to just do it in one place. So this one was an example. I removed it. This one was example of global explanation, right? And then if you want, you can actually see prediction like sample by sample, right? So in this case, I am calling this on patient ID 0 on my test set, and this tells me that base prediction for every patient is is $13,000 to $30, which is base value here, right? This would match with the mean that we calculated above in the notebook. And because this patient did not smoke, smoker is equal to 0, you are seeing that it is pushing it towards the lower side, right? And the cool thing about SHAP is all these numbers are additive. So think about if you want to build a waterfall chart, how does the prediction go from base value to X value? You can actually extract the data and build that, because if you will add them up, the maths would work. All right, what else? The other thing at this point I want to introduce is, if you go into your setup function and just say log experiment is equal to true, and let's just pass experiment name demo1, right? I'll run this again. So what this is doing now is, because PyCaret has integration with MLflow, what it's doing now is when you pass this log experiment parameter, it would initialize the MLflow process behind the scene and would log everything. And when I say everything, it would log hyperparameters of model, it would log all the metrics. If you ask for it, it would log the plots as well. And then the actual model artifacts, right? Let's just see. I'm going to start the MLflow server, this command here, and it would open up, hopefully, on your localhost 5000. There you go. And this is the experiment that we created, demo. This is the setup. Every setup would appear as one raw. If you click on plus, these are all the models that we train, right? So this automatically kind of becomes your, if you think about it, it becomes your leaderboard, right? Because it shows all the model, it has metrics. MLflow is really cool. If you click on it, you would see the hyperparameters of model, right? You would see the metrics, any tags, and you see the actual artifact, right? So if you want, you can just go ahead and download this pickle file. This is a pipeline that you can then load in any Python environment and use for scoring, right? MLflow also have a model registry. It won't work now. It needs a database behind the scene to work. So normally what you would do is you would set up a remote UI for this to work. Okay. All right. Going back, few other functions that I would show quickly is if you want to tune a model, right? Let's just create a decision tree model. Oops, not TD, DT, right? $3,383. I want to tune the model. Function is tune model DT. Now you realize how easy it is really to achieve these kind of things. So we have gone from 3,383 to 2,000. So behind the scene, we have created dynamic grids based on what model you pass. We bring up that grid and do random grid search, right? But if you want, you can pass your own custom tuning grid as well. By default, it uses random grid search from scikit-learn, but it has integration with 5-6 other libraries, so you can switch the search method. Instead of random, you can switch it to Bayesian, or you can switch it to teapot, you can switch it to a few other things, right? All right. Okay. At this point, we have a model, gradient boosting regressor, which is $2,700 in mean absolute error. We can check this is a cross validation score, but we can check the holdout score, 2,392, so a little bit less. Seems like cross validation score is a few $100s higher. It's not that big. I wouldn't bother, especially with the small data set. Something like this could happen, right? But when you are dealing with really large data sets, what you want to see is the scores on holdout set is close to your cross validation score. Okay. But if you want, you can, at this point, I don't have a new data. So what I'm going to do is I'm going to create a copy of this data and then drop the charges column. So I'm just simulating what a new data would look like, right? And then you would use a function called predict model, where you would pass this data, and boom, you would get your original data back and the prediction label, right? You can save this model, right? Let's call it my best model, and you would see it would save a pipeline. If I load this model so that I can show you what it looks like, this is a scikit-learn pipeline, right? We have a simple imputer. Even though we didn't pass it in setup, we have an imputer by default. As I said, if you have missing values, your model training will fail, right? So there are things that we do by default to ensure that your model training will not fail. We have categorical imputer, ordinal imputer, one-hot encoding, etc. And then at the end, we have our model, right? You can take this pipeline and deploy it into any environment where scikit-learn works, and it will work, okay? All right, if you want, you can deploy this pipeline, right, on AWS. I'll just say platform AWS. Hopefully this will work. Model name, my model 1, and you just have to pass the dictionary of your bucket name, right? There you go. So what it has done is it has taken your pipeline and transferred it to AWS S3. All right. And if you want, you can now in your process load that pipeline instead of managing the file yourself. Your experimentation process ends here, and in your deployment process, you can load this file, the model, back directly from AWS S3. Right. If you want, you can create an API endpoint. That's the most common way people would use. Right. You would create an API, my first API, right? I'm just passing my model and then giving it a name. And what it has done behind the scene is it has created a post API for you, right? I'm going to run this post API. It's using a framework called Fast API. Anybody used Fast API before? Sure, right? And if I run this, I would have a local host 8000 running. And because Fast API is built using Open API protocols, it is really able to generate this cool automated UI and documentation page, right? So you can see we have a one post API that was automatically created. This is the example schema that you would pass, right? If you want, you can just try it out, execute it, and you have your prediction back, right? What you would do at this point, let me really show you what happened behind the scene here, right? Behind the scene, we have created this Python file. This is the code that you would write when building an API using Fast API, what we have done is we have created this code, and this file is saved in your folder, right? And this load command is a little trick of Jupyter Notebook where you can actually display the files in the notebook, right? Essentially, it's a Python file sitting in the root folder. Okay. You don't have to stop here if you don't want to. You can go ahead and just also create a Docker image from this, right? Right. So now you have a, again, let me do the trick. Let me show you Docker file. This is the Docker file that we have generated, right? Obviously, it's just a file, right? If you have to build a Docker image, you'd have to copy this file and run it here. I'm not going to run it. It would take 20-30 minutes, right? But it basically, if you think about it, it takes you from, you know, passing your data for transformation up until your deployment endpoints, right? Few other things. Let me just show one more thing. So sometimes you may have a use case where you want to deploy your model where you do not have access to Python environment, right? Or on edge where you do not have access to internet, or you may have a latency requirement that the post API thing won't work for you, right? In a situation like this, there's a process called transpilation, which is where you take your model and convert it into other language, right? Which means that, let's just make it simple. Let's make a logistic regression first, sorry, linear regression first, right? And then there's a function called convert model, where you can just say, this is my model, take it and convert it into Java language. Let me add a print statement so it's more, right? So this is your Java equivalent code. Not really, you know, you not do this in an ideal situation, right? Because you don't want to hard code your weights, right? But imagine a situation where you don't have access to Python runtime, you don't have access to internet, you can't make an API call, right? For linear regression, it, you know, it still looks decent, right? But let me show you what happened if you do a tree-based model. You would get a 5 million lines of script, which is not really nice. Oh, we have LightGBM already. Let's just call it. Let me add a print statement, right? This is, you don't want this, right? And there are 7-8 other languages. You can do PHP as well. I don't know why would somebody deploy model in PHP, but yeah. All right. I think that's what I wanted to show you very quickly before. Are we on time? All right. I think we can go back to presentation. All right. So a little bit of shameless plug. I'm doing a masterclass tomorrow on PyCaret, where we will deep dive into a lot of technical topics for machine learning. So if you are transitioning into a data science role, or you're aspiring data scientist, it would be a good session for you to attend. All right, that's it. Thank you, everyone.